Okay, thank you, dear Presenter Praveen. Can you hear me?
Yes, we can hear you.
Okay, let's begin. Uh, Thank you for your introduction. Good morning, everyone. Every specialist in food science and nutrition. Firstly, thank Steve for giving me a valuable opportunity to present our research advances. Today, I will give a presentation on phytochemical profiles of whole grain rice and their antioxidant activity. The content of my presentation include these four parts. Part one, I will show research background. Firstly, let me introduce the definition of whole grain. The most common definition of whole grain from AACC. Whole grain shall consist of intact, ground, cracked, flaky, callus, whose principal anatomical component, the starch and the sperm, germ, and the brain are present in the same relative proportions as they exist in the intact callus. This is a typical sectional drawing of whole grain. Starch and spur account for 80 to 85% of the total weight, where germ is 3%, allulin is 6 to or 9%, inner and outer precamp are 4 to 5%. Antioxidant phytochemicals are mostly presented in allulin, layer, germ, and pericarp. Whole grain antioxidants are classified into two kinds according to the antioxidant mechanism. One is direct antioxidants with free radical scavenging capacity or reducing power, such as phenolics, vitamin E, carotenoids, gamma oryzanol, resistance phytic acid. The other one is indirect antioxidants without free radical scavenging capacities or reducing power in vitro, but could improve antioxidant status of human beings, such as co-factors of in vivo antioxidant enzyme or predecessor of in vivo antioxidants include minerals, trace elements, folate, protein, choline, sulfur, amino acids. The major phenolics in whole grain are benzoic acid derivatives and cinnamic acid derivatives. Uh, Benzoic acid derivatives include benzoic acid, p-hydroxybenzoic acid, protocatechoic acid, vanillic acid, salicylic acid, and gallic acid. And the cinnamic acid derivative include cinnamic acid, p-coumaric acid, caffeic acid, folic acid, and cinnamic acid. Whole grain phenolics are existed in both free and bound forms. Free phenolics could be extracted by organic reagents. Bound Phenolics are extracted from the residues obtained from the extracting from free phenolics. They are currently linked to cell structural components such as cellulose, hemicellulose, lignin, actin, and protein through ester or ester bond. From these two figures and the table, we can see like bound phenolics were major contributors to total phenolic flavonoid content and antioxidant activity whole grain. Bound phenolics account for 62 to 85% of total phenolic content of whole grain, and 61 to 93% of total flavonoid content of whole grain, and 58 to 90% of total antioxidant activities of whole grain. Cellular antioxidant activity assay was established by Dr. Rihadio in 2007. It was a more biological relevant method than the traditional chemical antioxidant assays, as it considers cellular uptake, distribution, and metabolism of antioxidant compounds. The best antioxidant method are animal or human study. However, they are expensive and time-consuming. In contrast, CAC is a cost-effective and relatively faster method for initial antioxidant screening of foods and dietary supplements. As shown in the left two figures, compared with the control group, decreasing fluorescence by the phenolic extract indicates antioxidant capacities. The right figures present the principle of CAC. Hepatitis cells was pre-treated with antioxidant compounds of fruit extract and DCFHDA. The antioxidants bond to the cell membrane and all pass through the membrane to enter the cell. DCFHDA diffuse into the cell where cellular hysteresis cleaved the diacetate moiety to form the monopolar DCFH, which was trapped within the cell. Cells was treated with ABAP, which was able to diffuse it into cells. ABAP decomposed to form a peroxyl radical. This peroxyl radical attack the cell membrane to produce more radical and oxidize intracellular DCFH to the fluorescent DCF. Antioxidants prevented oxidation of DCFH and membrane lipids and reduced the formation of DCF. The phenolic profile and antioxidant activity of commercially grown rice variety planted in northern, central, and southern area of China was investigated in our previous study. Food-free and bound phenolics of rice varieties were fully identified and quantified in this study. The effect of the three thermal processing methods, including cooking, improved extrusion cooking technology, rice noodle extrusion on phenolic profiles, and antioxidant activity of whole grain rice was evaluated in our previous study. The servo conjugated phenolics was fully identified and quantified, and their contents and antioxidant activity were decreased after processing. Execution would add nutritional value of products by increasing their content of bound phenolics. See our rice with different colors were evaluated, and black rice was highest in CA, followed by red rice, brown rice, and polished rice. Also, the free and bound phenolic of rice with different colors was fully identified and quantified. The previous study had reported that whole grain contained both free and bound phenolics. The bound phenolics are extracted from the residues obtained from the extraction of free phenolics. Most of the in vitro digestion treatment were conducted directly to the whole grain of products without the extraction of free phenolic. So the bioactivity, the bioaccessible phenolics contained both free phenolics that survival digestion and the phenolics released by digestion. However, the profile of digested phenolics released by the gastrointestinal digestion after extraction of free phenolics remain unknown. The present study was designed to determine the free, digested, and bound phytochemicals and their antioxidant activities of whole grain. Part 2, let me show the result we obtained. This figure shows the free, digested, bound, and the total phenolic content of whole grain. Whole grain samples include 3 brown rice varieties. Yeah, that's the LG25, LG26, and SG16. Wheat, corn, and oat. The total TPC ranged from 416 to 732 microgram. Digested phenolics contribute 57 to 79%. Free and bound phenolics contribute 12 to 17%, 7 to 25% of total respectively. High TPC in the digested fraction was due to the release of large amounts of peptides with amino acid, include tyrosine, tryptophan, and sulfur amino acid, cysteine, and release phenolic acid and flavonoids bound to protein. Early phenolics in whole grain was identified by UPRC Q-top mass. There were 13 phenolic compounds identified in whole grain. 8 monomeric phenolic compounds was identified by UPRC Q-top mass with authentic standards, and 5 dipheric acid was identified by a mass retention time and UV spectral as reported previously. 8 dipheric acid was first detected in grain. This figure presents a free, digested, and total phenolic compositions of whole grain. We can see that bond phenols were predominant forms in whole grain, followed by digested and free form. Bond forms are bound with several structural components such as cellulose, hemicellulose, and proteins. Digested forms are bound with proteins in their conjugated form. Free forms are presented in cytoplasm or vacuole. This figure presents shows the proxy radical scavenging capacities of whole grain. The PSC values of the total phenolics ranged from 32 to 125 micron. The bond phenolics had the highest PSC. It's 48 to 61%, followed by free. It's 14 to 36%, and digested phenolic is 6 to 24%. This figure shows the proxy radical induced oxidation of GCFH to GCF in H2 cells and the inhibition of oxidation by free fractions A, B, digestion fraction CD, and the bond fractions EF or less over time using protocol involving no PBS wash between antioxidants and the ABP treatment ACE and the protocol with a PBS wash protocol. CAA to remove antioxidant in the medium not associated with the cells in the no PBS wash protocol, the left 3 figure. The CAA determine the activities of antioxidant bound to cell membrane, and the antioxidants pass through the membrane to enter what, while in the PBS wash protocol, the antioxidants bound to cell membrane was washed away. So the CAA only determined the activity of antioxidants pass through the membrane to enter a cell. In the no PBS wash protocol, the CAA values of total phenolics ranged from 4 to 7 micromole. Bond phenolics had the highest CAA values, followed by its 63 to 78%, followed by digested. It's 21 to 41%, and free phenolics is 21 to 36%. In the PBS wash protocol, the CAA values of total phenolics were from 1.3 to 2 micromole. Bond phenolics contribute 47 to 57% of the total, whereas the digested and the free phenolics contribute 25 to 41 and 10 to 20% of the total, respectively. EC50 values are for the inhibition of proxy radical induced GCFH oxidation by quercetin and whole grain extract, and their cytotoxic concentration are shown in this table. The cytotoxicity results suggested that whole grain extract and quercetin showed no cytotoxicity to hepatitis cells at the tested concentrations of CAA. PCE principal component analysis. PCE was performed to evaluate the effect of parameters include TPC, PSC, CAA, and 13 phenolies in the classification and differentiation of free, digested, and bond fractions of whole grain. We can see that catechin, comaric acid, ferric acid, cis-ferric acid, and 5-diferric acid, PSC, CA were concentrated in the bond fraction. Synaptic acid and TPC was concentrated in the digested fraction, while hydroxybenzoic acid, vanillic acid, serinic acid was concentrated in the free fractions. Part 3, conclusion. In summary, the digested phenolics bound with protein in whole grain were firstly identified and quantified in the present study. We extended free and bond forms of phenolics in previous antioxidant research of whole grain to free, digested, and bond forms, and provide references for the release of different forms of whole grain phenolics in different parts of gastrointestinal tract. The three-step of extraction method of phenolics set up in the present study could be used as a reference for other researchers who want to investigate a complete profile of food. Part 4, acknowledgements. Thank you for the support from my research group and my principal investigator, Dr. Rogelio, thanks for his instruction and the forms I've got. Okay, thank you.
Thank you so much. Thank you so much for your wonderful presentation. So I'll leave some time here. If anyone have any questions or comments, you can please go ask Professor Eric Sheng.
May I have a question?
Yeah.
Yeah, okay. Yeah, I'm from Hong Kong. I'm Professor Wu. So very nice presentation. So I just wonder which part of the grain contain the highest content of antioxidant?
Oh, the arulin part had the highest content of phenolic compounds and antioxidant activities.
Can you see that? Which part?
Arulin.
Allure. Oh, yeah.
Yeah. Arulin part. This part, arulin.
Oh, I see. Just in the skin, right? In the
yeah.
Yeah. Okay.
Right.
Did you when you study the antioxidant activity and the content, did you separate the component of the grain? Or just did you separate this part from the grain? Or you extract from the bran?
Yeah, we separated and extracted the phenolic compound using some organic reagent.
Okay, yeah. So you first you separate the component first, right? You separate. You didn't extract the whole grain, or you extract only part, right?
Yeah, right.
Thanks.
Thank you.
Thank you, Professor. Thank you so much.